This lesson is going to continue with our discussion of limits. We're going to look today and focus on what happens when I try to find the limit of a rational expression, something like I've got written here, where you're talking about finding the limit of a fraction, and what happens when you get that indeterminate form that we talked about yesterday. So anytime you're evaluating a limit, the first thing you want to do is just substitute in your number, hope you get an answer. So I put in -2, I'm going to get -2 squared plus 3 times -2 plus 2 over -2 plus 2. But that's going to be 4 minus 6 plus 2 over 0. But that's going to give me 0 over 0. And that we talked about yesterday is that indeterminate form, which just means that, hey, you can't find the limit in this form. You're going to have to do some algebra or something to get it to something you can find the limit of. Alright, so let's go back, focus on our numerator, and what we should notice is that's something we know how to factor. So if we do the limit as x approaches -2 of x plus 2 times x plus 1 over x plus 2, we'll see that we can cancel out our x plus 2's. And yesterday we talked about that that's going to make a hole in your graph. Okay. When you have a hole in the graph, you can still evaluate the limit. What you're going to do, if you remember, this is what your function's going to look like. That's what your graph's going to be, but it's just going to have a hole. So if I take what's left after I've canceled, and now evaluate at -2, we get our limit. So the limit of the original function we had up here, we can now say that limit equals what we got down here once we factored and canceled, and we'd say our limit would be -1. Okay, let's look at one more example like that. Let's say we've got the limit as x approaches 3 for x squared plus 2x minus 15. If we put the 3 in, we're going to get 3 squared plus 2 times 3 minus 15 over 3 squared minus 9. That's 9 plus 6 minus 15 over 9 minus 9, and that's 0 over 0. Anytime you have 0 over 0, see if you can factor. So let's go back now. Factor that to x plus 5, x minus 3. And on the bottom, we'll factor to x minus 3, x plus 3. Now, the x minus 3's will cancel. And we're left with x plus 5 over x plus 3. Now let's do the limit of what we had once we canceled. Put 3 in. We're going to get 3 plus 5 over 3 plus 3, which is 8/6, which would then simplify down to 4/3. So we would say our limit would be 4/3. We're going to wrap up our discussion with the squeeze, or sometimes known as the sandwich theorem. Now, I want to point out that this is actually very, very difficult to prove. So we're not going to do any proofs. I'm just going to give you a general overview of what the squeeze and the sandwich theorem says. We're definitely not going to be looking at any proofs. Okay, first thing I want to do is let's use our calculator, and let's graph y equals the sine of x divided by x. Okay, let's check that we are in radian mode, and let's do zoom and then decimal. Okay, so here comes our graph. And when you look at the graph, it looks nice and continuous. And what I want to do is I want to talk about what happens if I look at the limit as x approaches 0 for sine of x over x. Well, if I do just substitution, I'm going to get the sine of 0 over 0, and that's 0 over 0. which again we talked about is called the indeterminate form, which means we cannot determine the limit in the form that it's in. So we're going to have to do something different. Well, this is where the squeeze theorem kind of comes into play. I do want to show you that this is not continuous. It's a little hard to tell it because of your axes being where the discontinuity is. If I go to second and zoom, I can turn the axes off. Right now they're on. But I can turn the axes off and then graph. And you'll just barely be able to see there is a little hole right there. Okay. Now let me turn the axes back on. So you can see where that's at. And you'll see that it appears that the hole is at 0, 1. Okay? So we're going to look at how can I prove that it actually is at 0, 1, which is where the hole is. All right, so here's what the squeeze theorem is going to say. Say that I have some function. Let me just go ahead and kind of sketch what we were working with. It's something that looked like this. We've got a hole. It's coming down here. And I'm trying to figure out what's the limit right here as x approaches 0. Well, let's call that function f of x. Say I find another function, let's say g of x, that is above that I know the limit for. We'll call that g of x. And another function below it that I know the limit for, and we'll call that h of x. So here's what I know. That f of x is between g of x and h of x. Well, if I know that the limit as x approaches 0 for h of x, let's say, is 1, and the limit as x approaches 0 for g of x is 1, then if these are both have a limit of 1, then the function in the middle kind of gets sandwiched into having the same limit, or you squeeze it into that same limit, and I could say then that the limit as x approaches 0 for f of x would have to equal 1. All right, so that's the whole idea behind the squeeze theorem, is that if you've got a function that you don't know the limit of, find a function that's bigger than that, or a function that's smaller than that, or similar, squeeze it between two limits that you do know, and if you know those limits are the same, then the one in the middle has to also be the same. Okay, that being said, you need to remember, this is a really important limit. The limit as x approaches 0 for sine of x over x equals 1. Again, if we look at it graphically, we were talking about the fact that there was a hole right there at 0, 1. So that hole is at 0, 1. So as you approach 0, that function is approaching 1. Now, that whole idea can actually be extended to say that if you have the limit as x approaches 0, let's say sine of 2x over 2x, that's also 1. Or the limit as x approaches 0 for the sine of 12x over 12x. That's going to be 1. Now what happens when I get something like the limit as x approaches 0 for sine of 2x over x? See, my property says that if it's 2x here, it's got to be 2x here. I have 2x, which means I need to have a 2x in the bottom. So here's what I can do. I already know I can kind of make common fractions, equivalent fractions, by multiplying them by the same term, top and bottom. So what I'm going to do is I'm going to multiply this by 2 over 2. That's going to give me this, 2 sine of 2x over 2x. But think of that as 2 times sine of 2x over 2x. But then if I do the limit, that's my special one. We said that that's going to equal 1. The limit of 2 is just 2. So I get 2 times 1. That's approaching 1. So that makes the answer 2. Okay, let's look at another one that's similar to that. Let's say we have the sine of 5x over 3x. I want the limit as x approaches 0. Well, the first thing is I could realize that that is this. 1/3 the limit as x approaches 0 sine 5x over x. All I'm doing there is taking this and thinking of it as a 1/3 times everything else, and then I can move the 1/3 out to the front. Well, we're in the same situation we were just a second ago. I've got sine of 5x over x, so I'm going to have to multiply top and bottom by 5 and 5. Well, if I do that, I'm going to have, let's bring this 5 out to the front, 5/3 the limit as x approaches 0 sine 5x over 5x. That's 5/3, and I now know that this goes to 1. 5/3 times 1 is just going to be 5/3. One last problem with that. Let's say I have the limit as x approaches 0 sine squared x over x. So if I start with substitution, that's always your first step when you're finding limits. If I put 0 in, I'm going to get sine of 0 squared, which I have to realize is the same thing as sine squared of 0 over 0. Sine of 0 is 0 over 0 is our indeterminate form, which means, hey, you got to do something else. Well, now I can't do like we just did a minute ago because this is sine squared of x. But what I can do is think of this as the sine of x over x times the sine of x over 1. So stop, look at that carefully. We now know that that goes to 1. And then this second part is just going to be times the sine of 0. But the sine of 0 is 0. So I have 1 times 0, which is 0. Okay, not going to lie, a lot of times these trig limits can get very tricky. Sometimes there's some weird little things you have to do to them. They take some practice, getting used to what to pair up together, but we'll get a hold of it and we'll get through it. And that's the end of the lesson for today.